The North Pacific is remote. Daring fishermen are usually the only souls to be found in this part of the world. There isn't much in the way of a human footprint here. The ocean is wild, teeming with birds, fish, and whales. Desolate volcanic islands dot the horizon, making up the westernmost regions of the United States. These are the Aleutian Islands and are a volcanic arc produced by the subduction of the Pacific Plate beneath the North American Plate. This subduction fault has been responsible for some of the world's most violent earthquakes, including the Good Friday earthquake of 1964. It registered 9.4 on the Richter scale and created a tsunami 67 meters high covering entire islands. During subduction, pressure builds along the fault line as one plate tries to slide beneath another. When the pressure is high enough, the subducting plate jolts forward and releases an enormous amount of energy, creating deep, powerful earthquakes that can be measured around the world. The whole fault line does not slip at once, but in sections. In the last century, virtually every part of the Aleutian subduction zone has slipped, save for one section in the middle of the arc. This section has puzzled scientists. Is the Pacific Plate slipping slowly beneath the North American Plate, relieving pressure as it goes? Or is it locked in place, building pressure to be released one day in a massive earthquake? To unravel these mysteries, scientists from Columbia University's Lamont Doherty Earth Observatory and Dalhousie University in Nova Scotia have embarked on a 6-week voyage aboard the research ship Marcus G. Langseth.
Chief scientist on board the Langseth is Donna Shillington. She studies marine seismology at Columbia University's Lamont Doherty Earth Observatory and began working on this project 2.5 years ago.
So many people around the world live next to plate tectonic boundaries, and the question that you always get is, when is an earthquake going to happen, or can you predict when an earthquake will happen? And in almost all of these settings, that's really the wrong question, because an earthquake will happen. And so the best thing to do is to be as prepared as you can. And one of the ways that we can be prepared is if we can anticipate how large of an earthquake is likely to happen and what style of earthquake will happen. And so what we hope to learn from this project is if we can use these kinds of data, seismic reflection data, to better constrain geohazards that are likely to happen. And so one of the biggest factors that controls how large of an earthquake will happen in a subduction zone is the area on the boundary between these two tectonic plates, which binds up and then moves in earthquakes. And so we want to use seismic reflection data from the Langseth to kind of map out that area. The big picture that we want to know is how large of an earthquake can happen in any given place. And there's a number of different ways that you can estimate that. You can look at how big earthquakes are that happened in the past. We can look at measurements of how the plates are moving now by using GPS measurements and other things like that. But what we hope to do is to use the data that we image to sort of estimate the area on the fault zone which can bind up and move in an earthquake. And this is sort of one of the factors you need to estimate how large of an event can happen in any given place. And so after we've taken these beautiful data that we'll collect from the Langseth, we'll be able to create an image of what the Earth looks like. And in particular, an image, hopefully, of this fault zone, which creates big earthquakes in this area. And look at changes in the properties of that fault zone in our data to figure out how big of an area might move in a single earthquake. Another hazard that we hope that our data will be able to help us better understand is the generation of tsunamis here. Past earthquakes in the subduction zone have actually had huge effects all around the world because they've created tsunamis which cause damage all along the western part of North America and even in Hawaii. And we'll be able to map out other faults that intersect the seafloor and might cause motion and affect the ability of this subduction zone to generate tsunamis. What we're doing is we're still using the same sound source of the Langseth, but now we're going to record it on a really dense array of sensors that are inside of these 2 8-kilometer long. And what these data will give us are really amazing pictures that are much more detailed. They'll show us sedimentary layers, we'll see faults hopefully, and because the source is large enough, as we hear, and because the streamers are long enough, we'll actually hopefully be able to get very detailed images of really deep features. And the main target is the actual plate boundary.
The The data is collected by reflecting sound off of layers within the Earth. The time delay between when the sound is produced and received by a hydrophone can then be adjusted to find how fast the sound traveled through the water and the Earth and how deep it went. These sound waves are created by air guns. Air guns are not actually guns at all, but devices that compress air and rapidly release it, creating a bubble that collapses upon itself, creating a pressure wave that travels through the water to reflect off various layers of Earth. Langseth carries 4 arrays of 10 air guns apiece. If the air guns are the mouth, the streamers are the ears. The ship carries 2 streamers, 8 kilometers long, each with the length, the equivalent of 87 football fields. The streamers are cables full of thousands of hydrophones. Attached to the streamers are cable levelers, known as birds. These birds have adjustable hydroplanes, giving scientists the ability to adjust the depth of the streamers. These streamers are optimally positioned for recording low frequencies and seeing deep into the Earth. However, these low frequencies are also utilized by marine mammals for feeding, socializing, and breeding. Thus, it's probable that the airgun signal may confuse and disturb echolocating mammals, hindering their ability to communicate socially, breed, or find food. In order to diminish these unintended effects, the ship carries protective species observers, or PSOs, on board. These PSOs stand watch outside every daylight hour and acoustically monitor for marine mammals 24 hours a day. If a marine mammal is spotted within a certain radius of the ship, airgun mitigation measures are implemented. Some species are so endangered, however, that airguns are shut down regardless of distance as soon as they are spotted. The long daylight hours of the Alaskan summer stretch the duties of the PSOs to upwards of 18-hour shifts per day, rotating between observation, acoustic monitoring, and data analysis. In addition to the PSOs, Dr. Shillington is accompanied by a cadre of other scientists and technicians working 24 hours a day to collect and process the data. Ship maneuvers, hard conditions at sea, and the complexity of the operations require technicians to constantly monitor equipment. Meanwhile, scientists pore over the data in order to recognize trends and points of interest that will influence the ship's course later on in the cruise. To assist in watchstanding and the deployment and recovery of scientific instruments, 5 undergraduates from Columbia University have embarked on board the Langseth. Hannah, Celia, Kelly, Jack, and Andy take shifts working in the main lab and lend a hand when they can. However, when there's downtime, life can be sweet. Baking, movie watching, working out, reading, and good conversation are the preferred hobbies of the undergraduates.
A lot of our motivations for bringing undergraduates to sea with us are actually really very selfish. We want to attract bright young people to come into our field and possibly pursue marine geophysics in the future. And this is a way that we thought we could introduce people, firsthand to what it's like to collect data and to start to look at those data and kind of what the experience is of being a marine scientist.
12 o'clock!
So, before you ever come out to sea, there's an enormous amount of planning that goes into a project like this, in terms of picking the right time of year when we can be here and the weather will be good, scheduling the ship, and organizing all the different parts of your experiment and planning something which is a reasonable and feasible experiment plan. And the people in the marine office at Lamont are absolutely critical in helping to put an experiment together and help us plan